Hello, good afternoon. My name is David Lučnej. I'm happy to welcome you at this installment of the seminar series of the Institute of Geology and Paleontology. Today, our guest is Dr. Daniel Garcia-Castellanos from Geosciences Barcelona, which is a part of the Spanish Research Council. Consejo Superior de Investigaciones Científicas, which is an institution similar to the Czech Academy of Sciences to some extent, or to a large extent. Daniel is presently a guest of the Institute of Geophysics of the Academy, where he is hosted by our new group or a new team of surface processes led by John Jansen, who actually has invited Daniel to join us for several months. And today the seminar was advertised as one devoted to both or one suitable for both students of soft rock, sedimentology and stratigraphy, and paleontology and earth history, because I believe the topic will be very interesting for all of you, for people from different disciplines. But before we start, let me just quickly give you a bit of background about Daniel. He has defended his PhD in 1998 in physics in Barcelona, and afterwards he went on for a postdoc research in the Netherlands, in Utrecht, was it? For 5 years, and since then he has he has done most of his research in Barcelona at the same institute. His attitude to earth sciences, to various problems of geodynamics, has always been deeply rooted in quantitative approaches and numerical modeling, starting with his PhD and continuing ever since. And the range of problems that he has dealt with is quite enormous, from modeling basins forming in response to lithospheric flexure, through geomorphology of subduction zones, more recently dealing with dynamics of lake overflow and spilling. He has been greatly interested in the interplay between the deeper seated lithospheric processes and what is going on the surface, and the mutual interaction of surface processes and the lithospheric scale processes. And today you will see an example of this approach on a topic that Daniel has been involved with for a fairly long time, which is the Messinian Salinity Crisis, the Zanglian flood. And I hope, or I'm sure you will enjoy it. Daniel, the floor is yours.
Thank you for these words. Very good summary, better than I could probably. I must start saying thank you all. I already said it the other time for hosting me here. I'm really having a great time. I feel like an honor and a pleasure to be interacting with so many interesting people, both in the geophysics department, university, as you know. As said, this is going to be my second presentation, and this related to this stay here in Prague. And this time I will deal with an issue that is a really, truly unique event in Earth history. It's actually an event that it's probably the most abrupt and intense in terms of energy dissipated the last 65 million AT boundary. Therefore, is a event that tests the ability of the Earth to the resilience to changes in the boundary conditions. I think this should be of big interest in future research, how the Earth responds to changing environment. Okay, this is on its own, but what happened is that about 6 million years ago, something went on in the Mediterranean, at the entire Mediterranean scale, and transformed that sea into a huge salt pan, where a kilometer-thick layer of halite was deposited in the bottom, and for a long time, what you would see as the sedimentary record is what you see images here, purely halite and gypsum in many areas. Let me show you that. This is the blocks falling from the first cycle of gypsum precipitation about 6 million years ago in southern Spain. Everything that you see in this picture is actually pure crystal, translucid crystals of pure gypsum, including the house itself. It's built with the same rock. So this is how they look like. They have several types of crystallization patterns, but usually they show this branchiated type of crystallization. The locals, they call these palm trees. And this, actually, there is a cave, Torbas, in this area I'm showing you, where you can walk underneath these first cycles, one of the cycles, and you can see how the nucleation of these palm trees, of these first gypsum branching trees, start nucleating. That's about gypsum, but where is the halite? Halite is also, it's only present in areas that have been pushed up by tectonic deformation. That's Sicily. This is a mine, gold mine in Sicily, near Aclea Minoa. It contains some potash. That's what brings these nice colors to the layers. But mostly it resembles, like you can see here, resembles white pure. Okay. It's working. Okay, so in that mine you can see things like these yearly cycles of about 15 centimeters in thickness, which already tells you about that the hydrological budget of the entire Mediterranean was similar to today's, because 15 centimeters of halite is about what you would precipitate from a saturated brine in with the present-day climatic situation in the Mediterranean. Every year, the Mediterranean is losing about 1 meter of water if it would be not supplied from the Atlantic or from the rivers. Yes. Yep. Yeah. You are not. It's not your eyes. Yeah. The miners, they excavate these figures in the virgins and all the stuff into the so it's okay. It's not you. So as I said, this you can see only in places like Sicily and Cyprus, where the tectonics have been pushing up all this, because halite is precipitating later than gypsum during the evaporation of seawater. So it's concentrated more in the central parts and the deeper parts of the Mediterranean basins. All these that I have shown, this was already known by these guys. Karl Mayer, he was the one who was defining the Messinian stage, and he was based on this recognition that at a similar period of time there were these outcrops all over the Mediterranean showing about evaporitic conditions. And Raimundo Sali was the one who was defining the Messinian Salinity Crisis concept. And he already knew about this because in his times, there were this proliferation of seismic surveys providing cross sections of the underground across the sea and showing this layer of relatively transparent facies that is related to halite. And halite behaves as a viscous fluid over geological time scales, and that's why it produces this diapir. So it was easy to recognize that there was this halite layer that you can see in Sicily. It was also present in the depth of the sea. So slowly, with the proliferation of these seismic techniques, a map has been developed where you can see that halite is concentrated in the center of the basins, whereas gypsum is more in the outer parts. Today, this is a recent paper that is compiling all these available seismic surveys, and this gives a very accurate vision of what is the distribution of these Messinian deposits. As I said, well, the scale is in meters, so in some places you can find deposits that reach nearly 4 kilometers, especially in areas where subduction is squeezing this salt and is piling up the salt near the subduction trenches. So the overall stratigraphy that has been inferred out of all these surveys is different for the Eastern and the Western Mediterranean. In the Western Mediterranean, you have this trilogy where you have halite covered by post-halite, post-salt deposits, and these have been drilled, and they show that they are reworked gypsum from the margins. So it seems like gypsum was exposed in the margins and then delivered and redeposited on top of the halite. So this means that after the initiation of halite precipitation, the seafloor, or at least the margins, were exposed and to the effects of erosion. The thing is different in the eastern basin. There you have only halite, and there is clear erosion surfaces on the bottom and the top of that layer. Okay, all this was, as I said, vaguely known in the 60s, and then it's by the late 60s when these three guys, Bill Ryan, Kenneth Su, and Maria Bianca Chica, they made this proposal to drill for the first time in situ this deep basin halite, and they were very recognized for that because they found very exciting things, like for instance anhydrite, that is supposed to form normally only at high temperatures exposed under in subaerial conditions, but this sample here and this sample here are found in a drilling more than 2 kilometers deep today. So this needs an explanation because it's an area that hasn't been deformed tectonically, so you cannot explain that it's down there because of tectonic reasons. And therefore, this apparent crack in the salt core extracted from this drilling suggests that this halite, this salt pan, was exposed to the air. So that would imply, and this is how the authors interpreted this, that this was exposed to subaerial conditions at high temperature. Okay, so slowly the consensus about what is the stratigraphy of the basin is not easy, but let's say that the overall view I extracted from this recent paper related to our ETM project, Salt Giant, the overall view is that the primary lower gypsum is the first thing that happened in the margins, and then after that you have reworked deposits falling into the deeper parts of the basins. Then comes the halite, probably coeval with drawdown, and you see some discontinuities, some discordances within these different layers. And then the upper gypsum comes, and the upper gypsum it's interpreted as re-sedimented or diluted from the margins, from the primary gypsum deposited initially, this one here, in the margins, and transported to the deeper parts of the basin and redeposited there. Okay, that's about evidence for recording the Messinian Salinity Crisis. I will now continue to two more types of evidence: erosion and biological impact. And then I will move into what are the mechanisms that are responsible for all this. Well, about the erosion, this map is showing one of the features that are commonly studied related to the Messinian sea level drawdown in the Mediterranean, which are these valleys excavated during the lowering of the sea level. Because of the lowering of the base level of the Mediterranean, streams propagate upstream an erosional wave that, according to these authors, it propagates further upstream, that's in the vertical axis, depending on the area and the drainage area of those rivers. Okay, so that is a first hint that there was actually a significant lowering of the base level. That was first seen in the Nile Delta. These are very old papers that were the first to turn on this light about the incision in response to sea level drawdown. But let me show you, this is more recent. This is in the margin of Libya. And here we are looking at a valley that is about 200 kilometers upstream from the coast. And this is the Gulf of Sirte. And it reaches a depth of more than 500 to 750 meters near the coastline. So it's a very deep feature that you cannot explain by climatic oscillations during the Plio-Quaternary. By sea level fluctuations, I mean. This is not eustatic. There must be another explanation. This is an aerial picture of the area today. So all this is presently covered in sand. This is the result of prospection. My favorite example is this one in the Ebro Delta. So here we are in the coast of Spain. And this is the delta formed by the Ebro. And this 3D block, seismic performed in 3 dimensions, from there you can extract automatically the Messinian discontinuity, the discordance during the Messinian erosion surface. That's the name we use for it. And based on that and the coherence, you can actually perform on this data river geomorphology. You can see the meanders recorded, registered in this surface that you extract from this 3D seismic block. And you can actually see river terraces that would be otherwise very difficult to explain if it would not be subaerial transport. But because an alternative explanation that is sometimes cited for these features is that it could be produced by submarine canyons. But examples like this really make it very difficult to envisage such origin for these features. So this is part of the thesis by Hanneke Haida. She will soon be ready with it. What we do is we compile at the scale of the entire, this is Corsica and Sardinia, the Balearic Islands here, and the Ebro Delta I was mentioning before here. And what we do is we compile all these features that could represent coastlines, recorders of the past location of the coastlines. The problem is what you pick as a sign for coastline. You can choose either the extent of halite, the lateral extent of halite, how far does it reach from the deeper parts into the margins, or you can choose the distribution, the extent, the lateral extent of the upper deposits. And depending on that, you get different estimations of what was, by doing a flexural backstripping of those shoreline indicators, of what was the original depth of this sea level drawdown. How much did the sea level went down during the desiccation of the Messinian Salinity Crisis? As for the biological impact, I will show these three. First, this gap in the plant diversification that starts exactly around 5 to 6 million years ago, and that has an impact on the diversification of plants around the Mediterranean that lasts until the beginning of the Mediterranean climate, the formation of the present-day Mediterranean climate. So that's one example. Another is the impact that this had on the dispersal of mammals from Africa to Iberia, and as I show in this picture, from Iberia to the Balearic Islands, for example. So suddenly new species arrived there. This is not a conclusive argument favoring or ensuring that there was actually an exposure of the seafloor, because such mammal dispersals sometimes occur even if you don't have a direct connection. Like one happened before the Messinian event, similar dispersal, but there is no way to invoke a desiccation of the Mediterranean Sea at that time. So we have to take this with caution, but it still is an argument. And then you have the impact on the marine life, and there things are more impressive. Of course, during the Messinian Salinity Crisis, the fauna in the marine waters, in the isolated waters of the Mediterranean, practically vanishes. So it disappears, it goes to zero. But even before that, there is already a signature that is presently being studied by Constantina Archiadi. This is work in progress. And this is a very project that gives a lot of hope, because it seems that it will be able to quantify in a very precise way what was the impact of this isolation, progressive isolation during the Messinian period before the crisis, and how soon this process of differentiation or the effects of increasing salinity started in having an effect on life. And presumably that's also responsible, the crisis is itself responsible for the present pattern of lateral or east to west gradient in species richness that you see today in the Mediterranean. This is a fact that has been recently recognized. I just realized that this paper here has 1,700 citations. I saw it yesterday, checking the. So understanding where all this comes from is very important, and I think the Messinian Salinity Crisis had clearly a role in starting all this. There are many open questions about the Messinian, but I don't have time to go through all of them. I will concentrate on the last one, as I said. What is the mechanisms? What are the mechanisms related that responsible for this isolation of the Mediterranean and the later restoration of normal marine conditions, because everything ends pretty sharply. All right, so about the mechanisms, what could cause this isolation? Clearly, the Mediterranean is a high salinity sea today, but this salinity is not enough, is not even close to precipitation of any salt contained in the sea. In order to isolate the Mediterranean, you need to narrow the Strait of Gibraltar. If you had the same configuration as today, you need to narrow it in order to, until you block enough the outflow of the dense, high salinity waters that go into the Atlantic. That's the important thing, more than the inflow. You can have a salt pan, you can accumulate as much salt as you need in a basin by just blocking not the inflow but the outflow, because that is what allows you to accumulate salt in your isolated basin. And to block the outflow, what you need, first of all, you need an evaporatic condition in your basin. So the Mediterranean is evaporating more than it receives from the rivers. And this ensures that the inflows are larger than the outflows. So as you reduce the size of this, then eventually you will only have space for the inflows to come in. And that's when the saturation or the increasing salinity starts in the sea. Oh yes, this is an animation of. Sorry for the music. This has been done by the University of Malaga. This is showing this interplay between the outflow in the Mediterranean and the inflow. And what you see is that at each tidal cycle in the Atlantic Ocean, it will spill fresh water or relatively fresh normal marine water into the Mediterranean, whereas the outflow is trying to escape. And you see that at each tide in this configuration, at each tide, this spilling of water caused by the high tide in the Atlantic side is impeding the outflowing waters, the deeper, denser, more concentrated waters from the Mediterranean to get out of the sea. Okay, you can see the interaction of these two layers of water in the surface in satellite images, and if you are lucky enough, you can even see it from the Strait of Gibraltar itself. Now, what caused? So we need something that closes the gateways, the last gateway between the Atlantic and the Mediterranean. What could it be? Well, the easiest option is a geodynamic event or a tectonic phenomenon. The tectonic context in the area is that the Tethys Ocean is progressively isolated after the breakup of Pangaea, eventually leading to something progressively more isolated from the rest of the oceans. That leads to this situation about 12 million years that I show here, where you have these remnants of the Tethys Ocean are separated now into two realms, which is the Tethys and Neo-Tethys area, or the present Mediterranean, let's say, and the Paratethys, what is called the Paratethys Sea. That is intracontinental as isolated basin with a completely different fauna. And as Africa and Europe continue approaching each other, then what happens is that the last connections in the Strait of Gibraltar and here, they close completely, and then you get this hypersaline condition in the Mediterranean basin. All right, and if you do the numbers, the funny thing is that we know, as I said, we know how much mass of halite has been deposited in the Mediterranean Sea. And if you do the numbers, you can estimate that actually you would need to evaporate about 14 to 22 times the volume of the Mediterranean in order to accumulate that amount of salt. So it's not just simply closing the gateway and letting the Mediterranean dry, but something must have lasted for quite long in order to isolate that outflow for time enough to accumulate this amount of halite. So we need something else. We need something that keeps the inflow open, but the outflow closed. And all that in addition to the eustatic sea level curves that should add some noise to that. What could that be? The explanation we were exploring is about the role of erosion along seaways. And so what we did is a 0D model. It's a very simple model that accounts for evaporation in the Mediterranean Sea and the erosion produced by the water flow entering the Mediterranean Sea. And for that, we use a very simple approach. We estimate the erosion as a proportional power law of the stress, basal shear stress. And basal shear stress is related to the sea level difference between Mediterranean and Atlantic. So the more sea level difference, the more erosion. And the more that's reflected in this S here, which represents the slope of the spillway into the Mediterranean. And another key parameter, of course, is also the erodability, this K here. So this erosion is erodability times shear stress. And putting that together in a model, this and I'm showing here time in the horizontal axis and elevation in the vertical axis. If you force a constant rate uplift, this will eventually lift the sill until it gets close to the Atlantic level, and then it will the sea level in the red line will go down because it is not receiving enough water from the Atlantic because the sill is too shallow. Okay, so eventually evaporation will produce a drawdown of the Mediterranean level, and this drawdown will increase the erosion capacity of these inflowing waters. So eventually the two things, the forced uplift, the prescribed uplift of the sill, and the sea level of the Mediterranean will find an equilibrium with one another, and that is what we propose might be keeping this inflow of water open, allowing salt to come in and accumulate in the Mediterranean for some period of time before the full closure takes place. So this would be an animation of this phenomenon. This is the sill being pushed up by tectonic forces, right? And every time the sill manages to close the inflow of water, then the Mediterranean goes down, and vice versa, right? And out of this competition, you get accumulation of as much salt as you need in the Mediterranean Sea. Now, what could cause these rates of uplift? And then to tackle this, we were going to tomographic data, as you can see here. This is a moving section across, you can see the location map here. So what it is showing is a slab that is a lithospheric slab that is attached to Iberia. Iberia would be in the left here. And it's attached to Iberia in the western part, but is detached in the eastern part. I'm going to show it easier probably here. This is a geological map puzzle with the same tomographic image. In blue, you have high-speed seismic velocities, and this is for 660 kilometers deep. So this goes deep into the mantle. And what you see is that there is a point, what we call the tearing point, that separates and the area where this lithospheric slab is hanging from southern Iberia, from the area farther to the east, in the right side, where the same slab seems to be detached. And the idea is that this detachment of a dense body of lithospheric slab that is detached in the eastern side, would be the cause for this uplift of the internal sedimentary basins that are isolated in the betics. The arrows are showing when the age in million years of these basins and how much did they move up. They moved up by several hundreds of meters in cases. So we think that detachment, this tearing of a lithospheric slab could be the reason why that was closing one of these last connections between the two oceans. Then we did some 3D geodynamic modeling to test this hypothesis. And what you see here is one of these slabs after a continental collision, where it starts under certain conditions that I don't have time to explain, but under certain conditions you can trigger lateral tearing of this subducted lithospheric slab. And what you see in the colors is the vertical velocity of this slab. The red is showing the fastest downgoing speed. And this speed is very negative, so it's downgoing in the beginning. And you see, the interesting thing is that at the same time that the slab is sinking, you get some areas where the slab is still attached to the upper plate, where instead of this connection to the upper plate is also pulling down the upper plate, where it is still attached to Iberia. So why is this important? Because this means that at the same time that you have uplift in the areas where it has been detached, you have some sinking in the areas where the slab is still attached to the upper plate. Okay, well, let me skip this, but the interpretation of all this is essentially what you see in this cartoon. The tearing, the lateral tearing, would explain uplift along one part of the orogen that is on top of that. That would be the Betic Riphean Cordillera in southern Spain and northern Morocco. And by the same process, because all the weight of this high density subducted lithosphere is now hanging only from the left side, then you get subsidence there. Okay, so the idea is that the slab tearing might be responsible for the uplift of the basins, and at the same time you are downlifting the area of the Strait of Gibraltar, and that would allow the later overtopping of waters, of Atlantic waters, that you need to explain why the Mediterranean is refilled. Well, this is an outreach video we produced some years ago already, that is explaining essentially the same story. This detachment of a piece of lithospheric slab. This was for diffusion in media and websites. So that the closure of the connection is leading to the evaporative drawdown of the entire sea. Okay. Now, how to refill the Mediterranean? I already gave a hint. Once you have the basin desiccated, you need something that brings some part of the divide between the Atlantic and the Mediterranean again down below the Atlantic sea level. And that's not trivial, because you just uplifted it. That's why that mechanism about the lithospheric slab tearing is important, because that one can produce simultaneously uplift and subsidence, which is otherwise would be difficult to explain. The fact is that the transition from all this Messinian record, the sedimentary record, to the Zanglian stage, it's very abrupt. So if you go to the original papers where these IODP drillings are described, sometimes you can put the finger on it, and sometimes it's only just a few centimeters. So something that geologically it's just instantaneous. But this is not enough because instantaneous in geology can mean tens of thousands of years, and you would not realize in the record, right? But there are other indications that suggest that this refilling was not at a normal, geologically speaking, rate, but it was something unprecedentedly abrupt and rapid. The first one is these erosion marks that cross the Strait of Gibraltar. Normally, you would have this Messinian erosion surface all over the Mediterranean, and that's not needing additional explanation apart from exposure. But the problem is that here in the Strait of Gibraltar, this erosion pattern is actually crossing the drainage divide of the Gibraltar Strait itself, which is already weird from a geomorphological point of view. No? You need something that is capable of eroding beyond into the Atlantic Ocean. And it enters by more than 80 kilometers in places. I'm not showing these seismic lines, but this would be compilation of this Messinian erosion surface over the entire Alboran Sea. So this is Spain here, or Iberian Peninsula and Morocco. And this would be one of the seismic survey across this position, about this position. So this is the typical configuration of this erosion channel that we describe along the Alboran Sea. It's a trough, an erosive trough, about 400 kilometers long, 2 to 10 kilometers wide, and several hundred meters deep. And altogether, it makes more than 1,000 cubic kilometers of erosion. And this is what we proposed already years ago. I'm not showing those old results, but this is what we propose as the place through which the refilling of the Mediterranean occurred. And the thing is that to explain the size of this, then there is no way that you can explain that without a very rapid refill in less than a few years of the entire Mediterranean Sea. And that implies water discharges that exceed or approach to 100 Sverdrups, which is 100 million cubic meters per second. Okay, and so it's really a big thing that needs big evidence to be supported. Then the first evidence is this one, is what you see here, is this erosion trough that, as I say, crosses the Gibraltar Strait. But then we were looking for, more recently, we were looking for additional evidence that could test this independently. And the common invocation is what happened to all this sediment that I was just mentioning. If all this was eroded from the Alboran Sea, all these 1,000 cubic kilometers of erosion should be found somewhere else. So this is what we attempted to look at first by doing modeling and using seismic profiles also in the Alboran Sea and the Ionian Sea, and numerical modeling of water flow and transport of material. So first, let me show these models where we were experimenting by dropping particles of different sizes in an empty Mediterranean. This is again the Alboran Sea, and we are dropping grain sizes in the order of pebbles to cobble to I can't see it anymore. Okay. But this is changing. The biggest size are the green, and then it reduces until the blue colors. And what we expect, of course, is that as we expect, the smaller the grain size, the farther they can travel with the water turbulence driven by this inflowing waters into a lowered Mediterranean sea level. And of course, with sands, then these particles travel much longer, and they can go into the Tyrrhenian Sea, or they can even reach the Sicily coast. And another set of experiments we were trying is focused on what happens. That's the other frequent question, let's say, about this Zanglian flood hypothesis, is what happens between the East and the West Mediterranean, because you have a threshold there. So if the West Mediterranean is refilling very rapidly, at some point the waters must overtop into the Eastern Mediterranean. And this is what we were also testing by first identifying this very peculiar body of sediment with this distribution that you can see here. The characteristics of this sedimentary body is that it's made out of very transparent facies. Sorry, it's unit 2, very transparent facies, which points to a very non-sorted, chaotic body that is often seen as a sign for very rapid accumulation of sediment, because there is no layering, there is no organization in those deposits. One of our plans, well, this you can see more details in this publication, but we were trying to obtain the possibility of drilling these deposits, but unfortunately it has not been successful yet, using the geodesic resolution IODP facility. So we keep on doing modeling because that's more suitable. And in these experiments, what we are doing is we are modeling the extent of these low energy areas that may explain the extent of the sedimentary chaotic body that I was showing in the previous figure. And the other interesting feature in the very same area, I just forget to mention, but we are here. This is Sicily, and this is the Nato Canyon that I will show right now. This is the Nato Canyon. This is a very interesting feature because it is a very vertical wall with this horseshoe shape that it's underwater today. So this is about, here you have the scale. So I think this is about 2,200 meters below sea level. So this doesn't look like something that can be created subaerially normally in its special conditions. And it reminds very much to features like this one belonging to the Missoula floods in the Washington state in USA. So it's a typical feature of megaflooding, this horseshoe erosion and retreat of erosion during very high flows of very high discharge. In the case of the Missoula flood, we are talking of 10 million cubic meters per second to form those features that I just showed. And finally, another feature that we have found that might be linked to the Zanglian flood is the formation of this type of deposits right next to the place. Here we are in the eastern Alboran Sea. Okay, so again, this is Spain, Africa. And in this area, there is this volcano building right in the middle of where the flood was meant to go along, just right in the middle of the path. And right behind, in the lee side of this volcanic edifice, we have this feature that has been dissected by 3 seismic cross sections that look like this. So it's an elongated body of a few of 1.5 meters of thickness, and we are wondering if this could not be a typical lateral bar deposited along the way of this huge flood that was refilling the Mediterranean, similar to what we have seen in other outburst mega floods like the one in Altai Mountains. You see this bar here. This is gravel deposited under suspension conditions. So all this valley was filled with water only a few thousand years ago. And in the areas of low energy, you had the deposits of these lateral bars that are now dissected by a tributary that drains to the main river going here. But this would be a cross-section of what this looks like. So you have this tilting outwards sediments and suspension deposits that, well, John Johnson can explain better how this works, because I'm not really an expert of this. But this would be the cool thing that would be ideal to identify if we were able to drill these deposits one day. That would be really, that was our dream. And actually, DREAM was the acronym for our proposal, but it doesn't, it looks like the dream is failing so far. Anyway, so the take-home messages I want to leave you with is that salt giants in general, they form by the reduction of connectivity of very large basins. And this connectivity is very much controlled not just by tectonic processes or by eostatic sea level changes, but also by the erodibility of those seaways. So those seaways are important to understand and to constrain, because being so large, the Mediterranean basins like the Mediterranean, they need so much inflow water that as soon as there is a little bit of the level difference between the two sides, they will generate high amounts of erosion rates. The Messinian Salinity Crisis was primarily caused by tectonic uplift along the Gibraltar Arc in competition with erosion along the seaway. And a Mediterranean evaporitic drawdown implies large amount of erosion at the sills. So again, let me insist on this idea. If you have tens of meters of difference between two large oceanic basins, then you will easily exceed what typically the vertical motions that you typically obtain from tectonic processes. And if the difference in level becomes larger than hundreds of meters, then any small amount of water that starts trickling from one basin to the other, from the upper to the lower, will easily develop into catastrophic water discharges and full refilling of the basin. And final one about the flood itself. Catastrophic flooding implies a previous large drought in the Mediterranean, for the reason I mentioned before. So those two things go linked together. And flood deposits can validate and refute the flood hypothesis, the megaflood hypothesis in the Mediterranean. We need to really touch those. We need to drill them. This is what we are aiming at. And because we have at least found these two sets of deposits in the Alboran and Ionian seas that are compatible with typical megaflood deposits. And that's why we need to independently assess this with drilling. That's it. I just leave you with another movie.
Thank you, Daniel, for a great talk, covering some really mind-boggling issues in earth science. I believe we now have time for questions, and there will be many. We will just need to use the microphone for questions. So please give me some time to run to you when you raise your hand. Yes, Jan?
Yeah, I would like to have two questions. Well, sorry, one question, but it is based, if I understood well, the tectonic uplift had to undergo two different speeds, because the first part of the uplift needed to still fill the Mediterranean Sea with salt water from the Atlantic Ocean enoughly to make there so thick deposits of the salt and gypsum and these stuff. And then the tectonic uplift had to be speeded up to completely close the Gibraltar, if I understood well, right?
Just a sec.
Yeah, no, that's exactly how it is. Either you have some acceleration of the uplift that eventually manages to block fully or to exceed the effect of the uplift. Sorry, the other way around. So either you have an acceleration of the uplift that eventually exceeds the erosion capacity of the inflow waters, but you could also have some minor lithological change, because I didn't mention that, but this erodibility is they can change in many orders of magnitude from one type rock type to another. But even just the fracturation of the rocks, they can change easily by orders of magnitude the strength of the rock. So if just during this uplift, the erosion produced by the inflowing waters reach a harder level, that would already in itself explain the full closure of the Mediterranean.
Thank you. We'll just do one little adjustment to the other microphone because we now have a mechanistic explanation of the problem with the mic. It's upside down. Here we go. So I don't need to run around like the headless chicken for the next questions. Do we have more? Yeah, okay.
Thanks, Daniel, for a great lecture on really complex issues. I'll have a pretty simple question. I believe that you've probably addressed that in some of the papers that you referred to, but you haven't actually stated that. What was the time scale of the Zanglian flood? You know, how long did it take for the flood to refill the Mediterranean basin?
Yeah, yeah. Sorry, I didn't show more results because it's already 10 years old, and I feel a bit ashamed of repeating over and over. But yeah, in that paper, we were estimating based on the size of this erosional trough that crosses the Strait of Gibraltar, which is at least 200 meters deep. Then the experiments we were doing were coupling, in the same way that I was showing, coupling the erosion of the inflowing waters to the refilling and the enlargement of this seaway that is allowing the water come in. And let's say the final situation of this, the final time of this model, it must fit the final size, the present size that we see in this erosional trough. And what we found is that there is no way to fit that size unless you have a very rapid catastrophic like discharge, as I said, in the order of 100 million cubic meters per second. And that means that, if I remember the number, 90% of the refill of the Mediterranean took place in less than 2 years. That was the number we were given in the paper. And truly, the underlying assumption behind this figure, the important one is, as I said, that this hole that we see today is all covered by sediment because there has been 5 million years of sedimentation on top, no? But all this erosional trough that we see, if that was caused by the inflow of water into the Mediterranean, and we see no other way to explain that, then the magnitude must have been in the order of these 100 verdrups I was mentioning. So 2 years, it's just a flash.
Thanks. Another question there? Okay.
Thank you for the presentation. And I have just a technical question, not a scientific one, but I will find help for your reconstruction and the videos and GIFs. So I wanted to ask, like, do you do that yourself, or do you have like people who do this? I don't know, reconstruction, because I think for the science communication is amazing. You have several of these, so yes, I noticed the references, but it's really amazing.
You mean like this one?
Yes.
Yeah. Well, this in particular was done by the University of Malta. I forgot to say, but it's written there, and it's associated to one of the paper where we describe the features along the Malta escarpment that I was showing. This Nato Canyon with the horseshoe shape that we think might be the result of megaflooding. But neither me nor Aaron Mikhaev we did anything like that. You know, you just talk to a professional who can do these things. They do it actually very fast nowadays.
So you have professional like this at your university or
Not-
at the University of Malta?
Not really. No, we don't, and I don't think Malta University has it either. You just hire someone because there are
Yeah.
many people who is just independent workers that are working on this, and that's easy because you will need this. I don't know. I just made this too, I think, in my life. No. Yeah. Thank you.
Okay. Further questions? John?
Thanks, Daniel. I was thinking, I didn't realize that it was such a large volume of erosion, actually. So I wonder if, is it possible that there was an isostatic response, excavation of the trench and deposition of the fan? Would that have driven a negative feedback to closing off the outlet? Is it enough or is it not enough?
Closure, the inlet of
Yeah,
of what?
so the gorge
Yeah.
at the strait was cutting, you say, a
Yeah.
couple of 100 meters.
Yeah.
And inboard was a fan. So was there potentially a kind of tilting effect, an isostatic tilting, or just
No.
not enough?
It makes complete sense. Actually, there after a few years after our study, there was Jerry Mitrovic. You know him. So he's working on glacial-isostatic processes, and what they were doing, because the timing of this closure of the Mediterranean and the cyclicity that we were obtaining during this competition between uplift and erosion along the seaway, along the seal, the timescales of that are in the order of a few thousand years, and that is comparable to the timescales of glacial-isostatic readjustment, as you suggest. So what they were doing is they were coupling to our model, adding on top of it the glacial-isostatic response, not exactly to what you say, so not to erosion itself, but to the sea level changes related to this competition. So this, you remember this out of phase evolution of the seal depth versus the Mediterranean Sea that I was showing. They were coupling the glacial-isostatic response to that to see what would be the effect, and they saw a variation in the frequency of these oscillations that would modify the values we were obtaining significantly. I mean, I don't remember the numbers, but it was more than a 20% or something like that. But that's really not important to us because we don't really know. We have no observations that allow us to detect those oscillations in the field. So far, we haven't. So, what do you say? What you say? The role of erosion is more important regarding the reconstruction I was showing. These maps of reconstructed paleotopography I was showing by my student, and she's actually having into account the weight of all the plio-quaternary that is deposited on top of these paleo shoreline markers that we identify, and she's doing a kind of a back stripping to bring back those paleo markers to their original, what should be their original position at the time, because that to have a more reliable estimation of what was the original sea level in the Mediterranean. So there it is certainly important, and we cannot do it perfectly because we know the weight of all those sediments, but all those sediments come actually from the continent, and we have no way to know what distribution those sediments have in the rocks in the continent where they come from. And that is also changing the isostatic balance, you see, because so we are just, when going back in time, we are just taking out the plio-quaternary and everything goes up. So our shoreline markers move up. But if we would do it perfectly, we should put all that mass that we have removed back into somewhere along the Pyrenees or the margins, because they have been eroded from there. But since we don't know the original distribution, there is no way to do it. Not even with models you can. You mean the ones during the Messinian? Yeah, but that's a different thing, because during the Messinian, in the large scale, the erosion that you have is not so dramatic. It will not have a big isostatic impact in general. For instance, the halite layer is mostly pure. It contains a small percentage of plastics. So that the Messinian, the salinity crisis is only 600,000 years in duration. So you don't have, and the drawdown is, we don't agree. So the community is completely divided on how long does it last. But it's certainly much shorter than these 600,000 years. So it's a very short period in terms of landscape evolution at the scales that we are talking about, the scale of the entire Mediterranean. Sorry,
Okay.
my answer might be a bit confusing, but let me give an example. Like when I did some experiments, for instance, to see what would be the effect of lowering the sea level in the Western Mediterranean and then allowing rivers to retrogressively erode and capture the continents next to. This was in the Ebro margin in eastern Spain. And I was modeling the entire Ebro basin story. And adding or not adding this drawdown that lasts for only a few tens of thousands of years, or maybe 200,000-300,000 years, changes nothing in the landscape evolution of the entire Ebro basin scale. Too short.
Okay, thank you. Okay, before I give it to Jan, may I ask a typical question by a sequence historiographer? And I admit that much of my question actually is based on my ignorance of the regional geology of the Mediterranean. But other than the paleo valleys, are there other signs of low stand of the sea level low stand during the desiccation, such as low stand shorelines and low stand deltas or forced regressive deltas around much of the Mediterranean?
Yeah, I did not have time to show, but there is this. There is a fantastic paper in Geology about 3 years ago. What the first author is Madoff, I think Madoff, and they show beautiful patterns of that are just atop the halite layer, of distributed delta systems that with even you can distinguish the lateral next to what was the water flow. You can see the dikes next to the positional dikes next to it in very much with a lot of detail. Really very interesting. I can pass you the article. But these have been also questioned by some people because they say the same features you could explain submarine as submarine features by turbidite delivery of transport to the abyssal areas. I think this is the most difficult aspect of the erosional features, is how to distinguish them, how to tell whether they are subaerial or submarine. And it's less trivial than it seems.
Okay. Maybe one last question from Jan. We need it for the people online.
Okay, I would like to ask if, for example, the reflooding of the Mediterranean had somehow affected the global ÚSTAV, and if, for example, in other delta systems, some progradation or subaerial erosion can be seen or something. If
some progradation in
the other deltas, like I mean, connected to the global oceans and the ÚSTAV of global ÚSTAV, if like the refilling of the
Yeah.
Mediterranean has affected the sea level in the world ocean.
Yeah, actually, there is a very neglected paper that is describing exactly this. They have an atoll in the Pacific Ocean where they see at the end of the Messinian Salinity Crisis, or the dates at the time were not very well fixed, because that was before the final datings of the Messenian Deposits. So what we now know that it should be around 5.3 million years ago. This is when the Mediterranean recovers normal conditions. They find in an atoll in the Pacific Ocean some signal in the seismic stratigraphy suggesting a lowering of the global ocean of about 30 meters. I think they say 30 meters, but actually the one you would expect from desiccated the Mediterranean to the levels that we think it was desiccated should be less than that, should be about in the order of 10 meters. So 10 meters, answering your question, 10 meters is the amount of global sea level drop that allows you to refill a Mediterranean that would be around 1.5 kilometers below sea level, present sea level. Yep.
All right, and there's a question from John again.
Thanks, David. This is a really silly one. You showed a plot, Loget's plot, of drainage area and nick point speed.
Yeah.
Right? Now, like you said, it's a mystery about how long we had the drawdown. There's not agreement. I can't remember if I asked you this before, but anyway, I wonder if because the nick point speed is scaled to drainage area, that means that only the big rivers can push a nick point above the high stand in the time that they've got. The small rivers won't be able to because their drainage areas are too small, the nick points will be too slow. And if you could use that as a threshold to back calculate the time of the low stand. Do you know what I'm talking about? No.
I think you could actually draw a sketch, illustrate your question. I mean, for the students in the audience, you probably are getting lost.
Okay, yeah, sure, I'll try.
That's going to be fun.
Because all of a sudden we have switched from a sedimentary geology and paleontology seminar to a geomorphology one. So
here.
Oh, yeah, there's a relationship between these two, and it's log-log, right? Now, this means that only big catchments beyond a certain drainage area or discharge are able to get their nick points above the position of the high stand when the Mediterranean refills. And the smaller catchments don't. And we can see that because only the big rivers have paleo valleys. The small rivers don't, because the nick point the nick point is flooded.
Yeah, but how do you say you would estimate the duration of the drawdown based on this?
Well, I think Greg could do it. We would have to make assumptions about this speed. Do you know what I'm saying, Greg? Is it crap? Yeah. Yeah, because there should be a threshold. This.
Just using, maybe these are the authors that have studied this the most. I don't remember I have seen anything like that. By doing it by modeling, by landscape evolution modeling, you end up with too many unknowns in the parameters. So those models have no predictive value. So I have seen, like, these authors and also Gargani and myself, we have been doing models that simulate this upstream propagation of erosion along the main rivers. But we have no predictability in the sense that we cannot use those models to decide how long does it last. And the reason is because the erosion parameters, essentially erodability and the powers in the stream power law, they are too unknown. You don't even have a 2 orders of magnitude range that you can attach to. And from that make some assumptions on the duration, you see? So, yeah.
Okay. Thank you, guys.
Do you agree with?
This was an unexpected excursion into quantitative geomorphology by some of our friends, including Martin Margot over there from the Department of Physical Geography and Geoecology. And let me just tell you that if you want to understand this, which is cutting edge geomorphological science, I'm sure you will be very welcome at lectures at the Department of Physical Geography. But sorry for interrupting that bit of the discussion. We now have about 10 minutes to vacate the room, so let's have a last question if there is anybody to ask one. And if not, we can always continue the discussions in a less formal manner. I think Martin Košťák is taking us to a restaurant facility somewhere and Karla, I guess. And was there a question to? Okay. All right. Thank you very much. We'll certainly consider that option. And with that, I would like to thank you all for coming. And above all, let me thank to Daniel for his great talk, very thought-provoking, informative, and also amusing. So if you want, you have, I think, on our website of the Institute of Geophysics, you can find Daniel's email address, so you can ask him if any further questions arise later on. Thank you.
Thank you. Thank you.